So the first thing is I won't be here on Monday. There is going to be a substitute here, and I gave them problems for you to do. I can't remember what it's like numbers 4 and 5 or something, just from the daily assignments. So if you come to class on Monday, you can work on problems during class with each other. It's helpful, you know. If you don't want to come, no one's taking attendance or anything, but it is nice to get a chance to work with each other on it, you know. But the substitute isn't going to know anything about how to do these problems. It's like a chemistry person or something. Okay, they can help you with chemistry, but okay. And so now I want to talk about solving systems of linear equations. You can always do this the same way, and all of your calculators do it. And the approach is called reduced row echelon form. And it's almost always abbreviated in things RREF. And the way it works is like this. So let's say we have, I'm going to do a system of 3 equations for 3 variables. So let's say we have negative 2x, I'm just totally making these up, plus y minus 4z is equal to 30. 3x minus 2y minus 20 is equal to 0, and y plus z is equal to 10. Okay. The first step is to create what's called the augmented matrix. And if your system, so for a system of n equations for n variables, your augmented matrix is going to have n rows and n plus 1 columns. Okay, and to create it, first, get all your variables on one side of the equation and your constant on the other side. And the constants just need to be alone on the other side. Then choose an order for your variables. And then each row of the augmented matrix represents one equation. Each of the first n columns represents a variable. Columns. Well, we have n variables, but we have n plus 1 columns. So the n plus 1 column represents those constants. So let me show you how to do this in the equations above. So for the example above, these are 3 equations. First, I'm going to make sure that the variables are on one side and the constants are all on the other side. There's only one of these that we have to adjust. So this is going to be negative 2x plus y minus 4z is equal to 30. That's the first one. The second one says 3x minus 2y is equal to positive 20. Okay, move the constant over to the other side. And then y plus z is equal to 10. Now I'm going to make a matrix. This is 3 equations for 3 variables. So that says that my matrix is going to have 3 rows. Each of those rows represents one of those equations. And my columns, I'm going to have n plus 1, so I'm going to have 4 columns. Okay, this represents equation 1, equation 2, equation 3. We have to choose an order. Everyone choosing an order here would choose the same order, X, Y, Z, because of the alphabet, because of alphabetization. But you don't have to. We could do Z, Y, X, or whatever. You could do any order you want, but I'm going to do X's, Y's, Z's, and then this last one represents the constants. And now I'm going to go through these equations, and each one of these spots is going to be the coefficient for that variable. Okay? These are linear equations, so we're not ever going to have the variable squared, cosine of the variable, anything like that. It's just going to be a number times the variable. So we're always just putting numbers in these spots. So for equation 1, the x's, we have negative 2 of them. The y's, we have 1. The z's, we have negative 4. And the constants over on their other side, we have 30. The second equation, x's, we have 3. Y's, we have negative 2. Z's, we have 0. And the constants, we have 20. And then the third one, x's, we have 0. Y's, we have 1. Z's, we have 1. And constants, we have 10. Okay, so now you just have to get this into your calculator. And the different calculators, you do this different ways. You all have TI calculators, I think I remember. You can also do this, by the way, in Wolfram Alpha. So if you just type RREF into Wolfram Alpha into the search bar, it'll bring you to the place, and it's pretty easy to figure out how to enter it. On TI calculators, if you have an 83 or an 84, you have to use the matrix environment. So you'll click on the matrix thing, you'll get in there, you'll go to edit, and you'll put this matrix in. I think maybe that's true for an 86 also. 84, I think that's true for an 86 too. I think for an 84, you can also use a notation like this, where you use a square bracket to denote a matrix, and then another square bracket to denote the rows, and then commas separate the values in the rows. So you could do this as -2, 1, -4, 30. Close the row bracket, start a new row bracket. Then 3, -2, 0, 20. Close the second row, start the third row, 0, 1, 1, 10. Close the third row, close the matrix. So this works for the 84. You also can do it this way for the 89. And then the 89 has another way that you just save some keystrokes, but where you just use a square bracket for the matrix, and then the rows, instead of square brackets inside this, are delimited by semicolons. So you can do this as -2, 1, -4, 30, semicolon. 3, -2, 0, 20, semicolon. 0, 1, 1, 10, close matrix. And then last is the inspire. And this one, you enter the matrix element by element in kind of a graphic formula. And I can't remember what it looks like, but there's a button that looks like a matrix or something. Click on that. It gives you some size options, and then you just go in, click, 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 click. Very like clicky, but it's nice and visual, so you don't end up entering stuff in the wrong spots or whatever. But then in all of them, once you have this, you just go R, R, E, F times R, E, F of that matrix, And it's going to give you a matrix where, so again, it's going to be n plus 1 columns and n rows. The first n by n matrix, if it works, if nothing went wrong with your calculation, is going to be the identity matrix. And then this last column is going to be the variable answers in order. Okay, so if you have an Inspire or an 89, there's also another linear equation solver, but you can always do it in reduced row echelon form. For the example above, okay, so we have our augmented matrix. So I'm going to enter that into, I have an 89. And so I'm going to go, my matrix is going to be -2, 1, -4, 30. Then semicolon, 3, -2, 0, and then 20. And then last 0, 1, 1, 10. And I'm going to use the store button to put this, to give it a name. I guess I'll put this in the spot A. And then I'm just going to go reduced row echelon form of A. See if this works. I've never tried this before. I just read about reduced row echelon form yesterday. No, I'm just kidding.
Someday you're going to say that to somebody who believes you.
Yeah. The people who have taken statics with me definitely do not believe that. And what I get is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so this is the stuff that only lets us know that reduced row echelon form found a solution. And then 21.82, 22.73, -12.73. So this is my answer for X. This is my answer for Y. And this is my answer for Z. Okay? Well, when I describe it like this, it feels like a long process, but when you get used to it, it goes really fast. And this system of equations is kind of on the border of like whether it's faster to just do substitution or whether it's faster to do this. But I guarantee as you get into these linkages, you're going to want to be using reduced row echelon form. As the number of equations and variables goes up, this becomes so much more efficient than trying to solve it by hand. Okay? All right, well, we did an example last time. So let me just remind you what that was. So we had this was the linkage. And we had a force of 20 newtons this way. And the lengths of both of these were 0.5. And the masses were 2 kilograms. And last time we went through all of Newton's laws and went through the rigid body analysis, and we went through the constraint equations, and we got a system of 6 equations for 6 variables. And so here's what they were. Our first equation was f12x minus 2a1x is equal to 0. Our second one is f12y minus 2a1y is equal to 19.62. Our third one, 0.25 f12y minus 0.0416 repeating times alpha 1 is equal to 0. Our fourth equation was 0.5 f12x plus, minus 0.16 repeating alpha 2 is equal to 5. Then the two constraint equations. Equation 5 says a1x plus 0.5 alpha 2 is equal to 0. And equation 6 says a1y plus 0.25 alpha 1 is equal to 0. And so now we just have to put this into the augmented matrix and do reduced row echelon form. Our matrix is going to have 6 rows and 7 columns. So my 6 rows are equation 1, equation 2, 3, 4, 5, 6. And for variables, I'm going to go f12x, f12y, a1x, a1y, alpha 1, alpha 2, and then these are the constants. So equation 1, f12x's, we have 1 of those. a1x, we have negative 2 of those. Everything I didn't fill in is a 0. These matrices are usually going to be pretty sparse, so you're going to have a lot of zeros. Equation 2, f12y's, we have 1. a1y, we have negative 2. Constant, 19.62. Equation 3, f12y, we have 0.25. Alpha 1, we have negative 0.0416 repeating. And then everything else is 0. Equation 4, f12x, we have 0.5. Alpha 2, we have negative 0.16 repeating. Bless you. Constants, we have positive 5. Equation 5, a1x, we have 1. Alpha 2, we have 0.5. And then the last equation, a1y, we have 1. Alpha 1, we have 0.25. And there you go. See if you can figure out how to enter this into your calculator, and I'll do it too. And so F12 those are the first two answers in that last row. That is, I got 7.5. Yes, 4.905. And then for the acceleration of the center of mass of body 1, I got 3.75 for x. This force is newtons, by the way. This acceleration, 3.75 for x, negative 7.36 for y. You're still matching? Yay. And then alpha 1 is 29.43 radians per second squared, and alpha 2 is negative 7.5 radians per second squared. Okay, so let's think about one thing that's pretty easy to visualize here is these angular accelerations. So let's see if these make sense. What we have is that body 1 is going to have a counterclockwise angular acceleration, and body 2 is going to have a clockwise angular acceleration. So if you look at this picture, does it make sense that body 2 would have an angular acceleration that's clockwise, and body 1 has one that's counterclockwise? Yeah, that makes sense. Okay. Any questions about that? All right, I'm gonna do number 16 from the homework, but really for the next, I don't know, week, maybe a little more than that, all the problems you're gonna do are just gonna be examples of this, okay? So that was on rigid body kinetics, right? It doesn't, and I'll show you why. Okay, so notice that So when we isolate the pulley, we're going to have a force here and a weight. But thinking about this angle first, so that's all I'm going to address here. We have this one tension here, I'll call that T2. And we have another tension here that is always going to be tangent, I'll call this T1, but it's always going to be tangent to that circle, okay? And so if you think about like the physics, the way you talked about moments in physics 1, what we really care about is the magnitude of that force times the perpendicular distance from the about point to where the force is applied. And notice that, so because this force is always tangent to that pulley, the distance to the contact point is always perpendicular to this. So it's always just going to be a moment that's counterclockwise, a positive moment that's equal to the radius times the force. Does everyone see that? Or everyone who cares? Does everyone who cares see that? Everyone's like, my mom just says I have to come to this class. Okay, so the angle doesn't matter. So might as well think of it as vertical or whatever, So the angle of the 600 Newton cable doesn't matter. So I'm going to just think of it as there's the pulley. Here's the 50 kilogram mass. And I have 600 going straight down. And I'm going to do part B. Anybody want me to do part A? It doesn't take very long. So I'm going to do it now where we're treating the pulley as having size and mass. So I'm going to start out with the rigid body analysis of the pulley. The rigid body kinetics for the pulley. Does this have a fixed point, the pulley? It usually fixed point means that you use that instead of the center of mass as the about point. In this case, they're both at the same location. So it's fixed at the center of mass, and that says that the moment of inertia is, this is just going to be the moment of inertia of a disk. So that's 1/2 times the mass of the pulley. That's a huge pulley, Jesus. 3 kilograms with a radius of 0.1. £7 pulley. Okay, well, we're going to get pretty different answers now, for this compared to the pulley without size and mass. We don't have to use parallel axis theorem because this is at the center of mass. So that's 0.015 kilogram meters squared. And now the free body diagram of the pulley. So I'm going to include, my free body is going to be all of the cable that goes over the top of the pulley, and just a, like a infinitesimal amount that comes off from the pulley, just so we can visualize it. So if I draw that free body, it looks like a little dog. There's the reaction force at the pin. I'll call that R. Bless you. There's a weight force for the pulley. That's 3 times 9.81, so 29.43 newtons. And then over here we have the pulling force T1. And over here we have the pulling force T2. And that's it. So now we can go to the table. I'll start out with R. That's a warm-up one. That one's easy. What's the vector from the about point to where the force R is applied? Everyone's like, I'm not answering that. That's stupid. It's 0. The force is R, X, R, Y. Cross product is 0. Same with the weight force. That is the same about point, same row vector. Zeros. The force is 0, negative 29.43. Cross product is 0. T1. The vector from the about point to where T1 is applied is negative 0.10. And the force is 0, negative T1. So the cross product is 0.1 T1. It says that that's counterclockwise. Does that make sense for that force? Yes. And then T2, the row vector is positive 0.10. That force is 0, negative T2. And so that cross product is negative 0.1 T2. Does it make sense that that's clockwise? Yeah.
Don't we already know the values of tension?
Oh, we already know it for T1, don't we? We don't know it for T2. This is 600. So that was, so this is the 600. So this force is negative 600, and that makes this 60. Do we need Newton's second law? No. So the moment equation says 60 minus 0.1 T2 is equal to the moment of inertia times alpha. And so I can write this as my first equation as, I'll do it as 0.1 T2 plus 0.015 alpha is equal to 60. And I'll call that my equation star. We're going to come up with this system of equations. We can't solve anything yet because that's one equation for 2 variables. So now I'm going to isolate the individual masses. I only have to do that once because we don't have a mass on the left side. So now I'm going to do a free body diagram of the mass we have a weight force down of 50 times 9.81, 490.5. And then a force up of T2. And so Newton's second law says 0 T2 plus 0 negative 490.5 is equal to the mass, 50, times this block is only going to move up or down, so I'm going to call this 0 A. I'll just call it A. We're going to calculate the acceleration of that mass. And so obviously the x equation doesn't help, but the y equation says T2 minus 50A is equal to 490.5. That's our equation 2 star. But we added a new variable, so we didn't make any progress. Now we have 2 equations for 3 variables. But now we're going to use the circular motion equation. And we're going to say that the vertical acceleration of the contact point on the pulley is equal to that A vector. Okay, so I'm first going to calculate the acceleration of the contact point on that pulley. That's circular motion. So that acceleration is equal to alpha cross r plus omega cross quantity omega cross r. Yep.
If the 600 force was created by a box.
Yeah.
And you wanted to relate to that other box, would that be negative A? Did people call that stuff?
Yeah. Mm-hmm. And yes, you would have to do that. Yep. All right, so let's fill these out now. Do we know? Oh, well, it says it's at rest. Really, that just kind of helps us, but it helps us sort of organize our thoughts. But we can do it no matter what that is, because that only comes into the centripetal acceleration, and we're going to throw that out in the end anyways. Okay, but this all goes to 0. Alpha is, we already have an expression for alpha, so this is 0, 0, alpha. And the r vector goes from the center of the circular motion to the point we care about. So that is positive 0.100. And so what we have is 0, A0, the acceleration of the mass, is equal to 0, 0, alpha cross 0.100. And that is 0, positive 0.1 alpha, 0. And so we get our equation 3 star that says A is equal to 0.1 alpha. I'll write it as A minus 0.1 alpha is equal to 0. This is equation 3 star. We don't care about this term anyways, so even if it didn't go to 0, we're going to throw away that centripetal acceleration.
Are we gonna be following this course for that doesn't happen?
Well, I mean, if I gave you a value of omega, that would be kind of like a mean thing to do. I mean, it would be testing like a real understanding that you have, but because you'd get an answer here, and then it would ask you to say like, oh no, how do I say that 0A is equal to something, you know, it doesn't make any sense. Well, the thing is that point on the pulley has a horizontal centripetal acceleration, but the mass itself doesn't have that horizontal acceleration because that cable, as soon as this thing starts moving horizontally, the cable just moves away from the pulley. Okay, so that would be a very belligerent thing for me to do on a problem, but really you should recognize that, okay, that part of the acceleration does not have to match between those two. Okay, so now we have 3 equations, 3 variables. Let's write these down. So 0.1 T2 plus, well, I'm just going to go straight to the, augmented matrix. We have 3 equations. Equation 1, T2s we have, oh, I gotta write the order, so I'll go T2, alpha, and A, and then this is the constant. So equation 1, T2s we have 0.1, alphas we have 0.015, constants we have 60. Equation 2, T1s we have 1. A's we have -50. Constants 490.5. Equation 3, A's we have 1. Alphas we have -0.1. Everything else is 0.